Imagine getting to London in 3 hours.
That's the promise behind this jet here, the Boom Overture.
Supersonic travel could be especially important for industries involved in medical transportation and disaster relief.
The control room goes quiet except for the hum of cooling fans and the soft click of keyboards. On the main display, a single line traces upward: altitude, velocity, engine temperature, climbing past numbers that, on paper, should not be survivable for a vehicle built from ordinary metal. Somewhere over a stretch of restricted airspace, an unmanned aircraft the size of a small fighter jet is accelerating through the part of the sky where conventional aviation simply stops working. It doesn't stop. It keeps climbing through the speed chart, past the point where standard jet engines choke on their own exhaust heat, past the region where aluminum begins to soften, into territory that for 50 years belonged to exactly one aircraft, and that aircraft has been retired since the last century. This is the story of how a small American company, operating on a fraction of the budget of a traditional defense program, built something that keeps forcing engineers to update what they thought was physically reasonable. For most of aviation history, speed and heat have been locked in the same argument. Go fast enough, and the sky itself becomes the enemy. Air molecules slamming into a fuselage at several times the speed of sound don't behave the way air behaves at highway speeds. They compress violently, they heat up before they even reach the metal, and they turn the leading edges of a wing into something closer to a blacksmith's forge than an airfoil. This single fact, that speed is ultimately a heat problem in disguise, has quietly ended nearly every serious hypersonic aircraft program the world has attempted. The company at the center of this story built its entire engineering philosophy around solving that one problem, rather than working around it. To understand why this matters, it helps to put real numbers next to the word hypersonic, because the term gets thrown around loosely. Mach 1, the speed of sound, is roughly 767 miles per hour at sea level, though the exact figure drops as altitude increases and the air gets colder. Commercial airliners cruise at around Mach 0.85, which is why a flight from New York to London takes 6 to 7 hours. Supersonic means anything faster than Mach 1. Hypersonic is the threshold engineers reserve for anything above roughly Mach 5 times the speed of sound, or something in the neighborhood of 3,800 miles per hour depending on altitude. At that speed, an aircraft covers close to a mile every single second. A flight across the Atlantic that normally eats up half a workday could, in theory, be finished before a single in-flight movie ends. For decades, the fastest air-breathing aircraft ever built was the State Route 71 Blackbird, a long titanium reconnaissance jet developed by Lockheed Skunk Works in the 1960s. It cruised above Mach 3, north of 2,100 miles per hour, at altitude so high that its pilots technically qualified for astronaut wings under certain mission profiles. It was a masterpiece of its era, and it was also, in its own way, a beautiful mess. The airframe ran so hot in flight that the fuel tanks were deliberately built with gaps that leaked fuel while the jet sat on a runway, because the metal panels only sealed properly once they expanded from the heat of flight. It needed a custom blended fuel, a dedicated fleet of aerial refueling tankers, and an army of ground crew to keep it flying. It never sustained true hypersonic speed. When the Air Force retired the last operational Blackbirds in the late 1990s, the general assumption in aerospace circles was that extreme sustained speed in the atmosphere had essentially reached its practical ceiling, and that anything faster belonged to rockets and one-shot missiles, not reusable aircraft. Concorde told a similar story from the civilian side. It proved passengers would pay a premium for speed, cutting the transatlantic crossing to roughly 3.5 hours at its cruising speed of Mach 2. But the airframe grew several inches in flight from thermal expansion, fuel consumption was brutal, the sonic boom confined its routes almost entirely over open ocean, and it carried barely 100 passengers per flight. After a fatal crash outside Paris in 2000 and mounting economic pressure, it was retired in 2003. Concorde never even reached the halfway point to Mach 5, and it still couldn't make the economics work. Between Concorde and the Blackbird, the aerospace world had two clear data points. Passengers would ride a fast jet, and a rugged airframe could survive near hypersonic heat for a while. Nobody had put both of those lessons together into something that could cruise at true hypersonic speed, do it economically, and do it again the next day. While commercial aviation actually slowed down after Concorde's retirement, airlines optimized newer jets for fuel efficiency rather than speed. Military interest in extreme velocity never went away. It simply moved into a different kind of hardware, missiles. Russia has publicly demonstrated the Avangard system, a hypersonic glide vehicle that rides the edge of the atmosphere while maneuvering toward its target instead of following a predictable arc. China has unveiled the DF-17, a ballistic missile that releases a hypersonic glide vehicle capable of skipping along the upper atmosphere and changing direction mid-flight. These aren't hypothetical laboratory concepts. They have been flight tested, publicly displayed, and described by their governments as operational. The problem this creates for American missile defense is straightforward and uncomfortable. Traditional interceptor systems were designed around predictable ballistic arcs, an object launched on a known trajectory that a defense system can calculate and intercept in advance. A maneuvering hypersonic glide vehicle doesn't cooperate with that math. It flies lower, changes course, and can arrive before a defense system has fully committed to a response. But according to public statements from defense officials and congressional testimony over the past several years, the deeper strategic gap isn't really about the incoming threat. It's about what the United States doesn't have on the other side of the equation: a reusable platform that can cross an ocean in under an hour, complete a mission, and fly home to do it again the next day. A missile is used once. What senior defense planners have repeatedly described as the real prize is an aircraft, not a warhead, fast enough that existing air defenses simply can't get to it in time, and durable enough to be flown again and again like any other jet in a squadron. That is the gap a small Atlanta-based aerospace company set out to close. Founded in the late 2000s by a group of engineers who had previously worked on high-speed flight programs for the U.S. Air Force and who had cut their teeth on other ambitious aerospace efforts in the private sector, the company built itself around a single conviction: the wall everyone kept hitting at hypersonic speed wasn't a law of physics. It was an unsolved engineering problem, and unsolved engineering problems eventually get solved by someone willing to iterate quickly and accept failure along the way. Their stated goal was not a missile, and not a one-off demonstrator built to set a record and then get mothballed. Their goal was a reusable aircraft that could cruise at Mach 5, take off from an ordinary runway, land, refuel, and fly the same mission again, for military reconnaissance, and eventually for paying passengers. The centerpiece of that effort is the engine, and the engine is where most outside observers underestimate just how strange the engineering challenge really is. A conventional jet engine is brilliant at everything from takeoff through moderate supersonic speed. Spinning turbine blades pull in air, compress it, mix it with fuel, ignite the mixture, and push the exhaust out the back. But as an aircraft accelerates further, the incoming air becomes so hot and energetic that those same spinning blades become a liability rather than an asset. Internal temperatures spike, efficiency collapses, and eventually the turbine simply can't keep up. A ramjet solves the high-speed side of that equation by removing the moving parts entirely. It's essentially a carefully shaped tube where the aircraft's own forward velocity rams air into the intake with enough force that the geometry alone compresses it. Fuel is injected, combustion happens, and thrust is produced without a single spinning blade. The catch is brutal in the other direction. A ramjet produces almost no thrust at low speed. You cannot take off in one. You cannot even get through the early acceleration phase. It only becomes useful once the aircraft is already moving fast enough to ram sufficient air through the intake on its own. The engine this company developed is designed to be both things in one housing: a turbine engine at low speed, transitioning into a ramjet-style duct at high speed, all inside a single unit rather than two separate propulsion systems bolted together. At low speed, air flows through a conventional turbine core, just like any other jet. As the aircraft accelerates, the airflow is progressively redirected around that turbine core and into a separate duct where combustion continues without any rotating machinery. On paper, that description sounds tidy. In practice, engineers who have worked on this exact problem describe the transition moment as the hardest few seconds in the entire flight envelope, sometimes referred to informally as the Valley of Death, the brief window where neither propulsion mode has full authority over the airflow, where the turbine is winding down its contribution while the ramjet duct is only just opening, and where a stall, a failure to ignite cleanly, or a pressure spike could mean catastrophic deceleration at exactly the altitude and speed where there is no room for a gentle recovery. Testing that transition on the ground, using facilities that can simulate the airflow conditions of Mach 3 or Mach 4 without ever leaving a hangar, took months of iterative work, and getting a repeatable, controlled mode switch validated on a test stand was treated internally as one of the most significant milestones of the whole program, proof that the Valley of Death could actually be crossed rather than just theorized about. That kind of ground testing, however, only proves a concept can survive in a controlled laboratory environment. It says nothing about whether the same transition can happen in real flight, at real altitude, with a real airframe shaking and flexing around it, which is why the company built an entire family of progressively faster flight demonstrators rather than jumping straight to a full-scale hypersonic prototype. The first demonstrator in that family never left the ground at all. A full-scale structural mock-up used purely to work out plumbing, wiring, landing gear, and the remote flight control systems long before anyone risked an actual flight. The next vehicle in the lineage was the first aircraft actually built to fly, a small, unmanned, highly swept-wing demonstrator powered by a proven, off-the-shelf turbine engine, designed specifically to prove that an airframe shaped for high-speed performance could still safely take off and land on a normal runway using conventional landing gear. That's a detail people underestimate. Every hypersonic concept eventually has to answer the boring question of how the thing gets off the ground and back down again without a mile of specialized launch infrastructure, and this early demonstrator existed to answer exactly that question. It flew successfully at a major U.S. test range in the western United States, validating the aerodynamic models and control systems the team had built in simulation. From there, the program moved into a larger, faster demonstrator roughly the size of a fighter jet, powered by a much more powerful and battle-tested turbine core, the same general family of engine that has powered frontline American fighters for decades, with tens of millions of cumulative flight hours behind it. This vehicle represents the bridge toward the eventual combined cycle engine, and its early test flights, conducted from a spaceport facility in the American Southwest using restricted military airspace as a test range, were explicitly described by the company as the opening phase of a broader test campaign meant to progressively push through transonic speed into supersonic, and eventually toward the edge of hypersonic territory. Each subsequent vehicle in the planned sequence is meant to go faster and carry a more complete version of the combined cycle engine, with the ultimate goal being a demonstrator that carries the full turbine to ramjet engine and attempts, for the first time in a reusable aircraft, an actual live mode transition in flight, taking off under turbine power, accelerating through the supersonic range, closing off the turbine's airflow path, opening the ramjet duct, and continuing to accelerate toward hypersonic speed, all in the open sky rather than on a ground test stand. If that flight test transition succeeds, it would represent something no reusable, air-breathing aircraft has ever demonstrated, a genuine turbine-to-ramjet handoff at speed, in the air, on a vehicle designed from the outset to land, refuel, and do it again. That single achievement is the hinge on which the entire rest of the program swings, because everything downstream of it, every application, every future aircraft, depends on proving that this engine concept works outside of a laboratory. Assuming it does, two very different aircraft sit on either side of what this technology unlocks. On the military side, the company has described a reusable hypersonic reconnaissance and strike support drone, roughly the length of a small business jet, intended to operate using the same hybrid propulsion architecture as the flight test demonstrators. Unlike a cruise missile or a ballistic weapon, this aircraft is meant to fly its mission and come home repeatedly. Picture the operational difference. Instead of a conventional reconnaissance aircraft spending hours slowly approaching a heavily defended coastline, trackable and vulnerable for the entire approach, a hypersonic drone departs from an ordinary airbase and covers a body of water the size of a major sea in well under an hour, executes its mission, and exits the area before enemy air defenses can mount an effective response. The speed itself becomes a form of protection. And because the aircraft is reusable rather than expendable, it can be tasked repeatedly, mapping radar installations on one sortie, carrying electronic warfare equipment to suppress those same systems on the next, all while the airframe simply returns to base and prepares to fly again. This directly addresses something American defense officials have said publicly for years: the need for platforms that can operate inside contested, heavily defended airspace without depending on vulnerable forward bases sitting on an adversary's doorstep. On the civilian side, the company has outlined plans for a small, roughly 20-passenger hypersonic airliner targeting sustained Mach 5 cruise, aimed initially at long overwater business routes, New York to Paris, for instance, compressed from a 7-hour flight into something closer to 90 minutes. Cruising at altitudes approaching 90,000 feet, nearly 3 times higher than a typical airliner, passengers would see the sky darken toward black and the curvature of the Earth become visible through the windows. Getting people through that kind of flight safely and comfortably is its own engineering discipline entirely separate from the propulsion problem. The acceleration profile has to stay gentle enough for passengers rather than a drone's flight envelope. Cabin pressurization and emergency systems have to be redesigned for an environment where conventional escape procedures don't apply. And none of that engineering work has been publicly demonstrated yet. There's also a regulatory wall standing entirely outside any single company's control. Since 1973, the United States has prohibited routine supersonic flight over land because of sonic booms, and any hypersonic airliner would face that same restriction unless the rules eventually change. Separate research efforts, including a quiet supersonic demonstrator jointly developed by NASA and a major aerospace contractor, designed to reduce a sonic boom to something closer to a soft thump rather than a window-rattling crack, are currently in flight testing and could eventually influence whether regulators revisit the overland ban. Any hypersonic airliner's civilian future is tied, in part, to how that separate regulatory question gets resolved. This company is not working in isolation, and it's worth being clear-eyed about that, because the broader race towards sustained high Mach flight has several serious competitors pursuing different pieces of the same puzzle. One California-based aerospace firm has already flown a rocket-powered reusable hypersonic test vehicle beyond Mach 5 in Pentagon-backed trials, dropped from a carrier aircraft, landing afterward at a U.S. Space Force base, a genuine milestone, though it relies on a rocket engine rather than the air-breathing turbine-to-ramjet approach at the center of this story. On the commercial supersonic side, a separate company has already broken the sound barrier with a small prototype aircraft, building toward a passenger jet aimed at roughly Mach 1.7, fast, but well short of hypersonic. And in a cautionary example of just how difficult this problem really is, a British engine developer spent more than 3 decades and enormous sums of money developing an ambitious combined-cycle engine with its own sophisticated air pre-cooling system technology that outside experts have called genuinely groundbreaking, only to run out of funding and enter bankruptcy before the engine ever flew on an actual aircraft. That failure isn't a footnote. It's the clearest illustration available of exactly how many well-funded, technically serious hypersonic engine programs have died before reaching flight, and it's the shadow every remaining competitor in this space is trying to fly out from under. What sets this particular American program apart, at least based on what has been publicly demonstrated so far, isn't a single dramatic breakthrough. It's the accumulation of unglamorous, methodical progress. A combined-cycle engine concept that has already shown a repeatable mode transition on the ground. A family of flight demonstrators that has actually left the runway, rather than existing only in wind tunnel data and computer models. A funded partnership with the U.S. Air Force that has survived multiple budget cycles. And a working philosophy: build hardware quickly, test it aggressively, expect it to break, fix it, and fly again, borrowed openly from the iterative culture that reshaped the private rocket industry over the past 2 decades, applied here to a field that has traditionally moved at the glacial pace of multi-decade defense procurement programs. None of this guarantees success. The hardest step in the entire program, a live in-flight transition from turbine to ramjet at actual hypersonic adjacent speeds, not on a ground rig but in open sky, still lies ahead, and history is not short on hypersonic programs that looked promising right up until the moment they didn't. But the trajectory so far is genuinely unusual for this field. A company with a fraction of the budget of a traditional prime contractor has taken an engine concept from a laboratory curiosity to a series of aircraft that have actually flown, on a timeline measured in a small number of years rather than decades. The Blackbird held its speed record for the better part of 50 years, largely unchallenged, in part because almost nobody was willing to seriously attempt what it took to beat it. Whether or not this particular company is the one that finally does it, the era in which extreme atmospheric speed belonged to a single retired titanium jet from the 1960s is clearly, finally, coming to an end, and when the record does fall, it won't be a rocket, and it won't be a one-shot weapon. It will be a plane that takes off from an ordinary runway, does its job, and comes back to do it again the next day.